So, welcome to the IMBS, and the rest of you, welcome to the IMBS. Hidden symmetries, inherent in decision methods. Now, actually, I have to give you one of my prejudices, and my personal belief is that symmetries and invariances are everywhere in the social and behavioral sciences. It's just that we don't know how to find them, and we don't know where they are. My belief is that once we learn where are these symmetries and how to get them out, they're going to prove to be powerful mathematical techniques that are going to allow us to advance our understanding of several of these areas. In fact, what happens is the goal of this lecture is to give one particular example. Emphasize one example to show you how symmetries, by understanding what's the underlying symmetries of the problem, a decision analysis problem, that we can now answer and pull together a wide, disparate literature. Now, the problem is, as I've already stated, is that we have to learn where to search. Where are we going to find the symmetries? And then how do we extract them? And, but I remain quite excited about the role and possibilities in this direction. In fact, I'm so excited about it that I actually have a t-shirt, a t-shirt that says symmetry groups on it, and I was going to wear it today, but it's in the wash. So what can I say? So what I did is I have a picture of me wearing it with my, while I'm exploring new retirement opportunities. New heights. Didn't think I could do that, did you? No, I mean symmetry in a very broad sense when I talk about this. For example, in society, in the social sciences, we have a constant tension between individuals and groups. We see this constantly. With regulations, for example, there are regulations for groups, but why should I have to wear my helmet, or why should I have to do all these other type things? And an area where we talk about different things is in game theory. And it turns out that there's some hidden symmetries in there. They're not obvious at all, but there's hidden symmetries inside whatever game you have. And the symmetry allows you to decompose games into explicitly the part that gives you the me part, what I can do on my own, and the we part, where we need cooperation. And with this, we're able to now get several new results in terms of game theory. This is joint work with Dan Jesse. When I say symmetry in a broad sense, I also mean symmetry of geometric objects. Symmetries of a torus, a donut, surface of a donut. And here we're learning that it provides, the symmetries of a donut provides us insight in terms of vision, split vision, in terms of the faces and things, color and color surround type issues, etc. And this is joint work with Louis Nairns. The ideas for this particular project are about 11 years old, 12 years old? Yeah, probably longer. We developed them. But Louis has a disadvantage of working with an irresponsible colleague who hasn't written down the theoretical proofs of it. They're coming, Louis. Okay. Voting theory. If you've ever just picked up almost any book on voting theory, you see all sorts of paradoxes. If you use such and such a method, A is better than B is better than C is better than D. You drop one candidate and it flips. And all sorts of things of this type. And in voting theory, what have we had? We've had all kinds of so-called axioms about what happens here and what happens there. And we have a huge, huge literature. And it tells us nothing. We now know that all of those voting paradoxes, all of those theorems, all of those different other things, really, quite frankly, can be explained with symmetry groups. And it turns out that with the right symmetry groups, you can take whatever project or anything else that comes up, and you can show where all those theorems are special cases of these different symmetry groups. So there again is an inherent part of symmetry, which we don't realize it's there. But once we realize it's there, it becomes a very, very powerful tool. I'm going today to talk about a special case of paired comparisons. The reason I'm talking about paired comparisons is that we use it a lot, particularly in Cog Sci. when you have your experiments and you're making paired comparisons with data. And so I'm going to talk about that and talk about its rich history. The history is so rich, it's impossible to talk about the whole history. So I'm going to just take out aspects of it. And I'm going to show that the many seemingly different approaches, in fact, can be all answered, and they're all special cases of one simple symmetry group. That's it. Now, let's start with something that doesn't seem to have anything to do with symmetry groups. Arrow's theorem. Okay? Now, I think most of you know Arrow's theorem. If not, I'll just give you a brief outline. Arrow wrote down 5 conditions. First, the inputs have to be transitive, well-behaved. Secondly, the outputs have to be transitive and well-behaved. We want good stuff. Then what he does is he throws down a couple of other conditions, and he says, once there's 3 or more alternatives, can't be satisfied. You're always going to have a trouble. One of the main conditions that Arrow has, and with that, we have come up with the statement that no voting system is fair. That's a common. So you hear it in the newspapers after there's a 3-candidate election that we get a weird outcome. And we read this with the Gore and some of the other elections. Well, there were 3 candidates and no voting system is fair with 3 candidates. That is really, they're referring to Arrow's theorem when they say that. Actually, it's a misinterpretation. The key assumption in Arrow's theorem is something called independence of irrelevant alternatives. It says that if all of us in the room here, we have 3 candidates, Anne, Barb, and Roy Moore, okay, from Alabama. What happens is that, let's look at the Anne-Barb relationship. That's going to depend on what everybody in the room, how you rank Anne and Barb. If all of you now start reading the newspaper about Moore and you change your opinion, it's a different profile. But if you have the Anne-Barb ranking the same, then they should be ranked the same. Okay? So that's Arrow's independence of irrelevant alternatives. But let's see what it says. It's easy to prove that IIA, that a voting rule or any other satisfies IIA if and only if you can write it as a paired comparisons, as a paired comparison for A, B, never mind what happens here, paired comparison for A, B, C, AC, etc. And so really Arrow's theorem does not, contrary to what we teach in our classes here at UCI and elsewhere, it does not mean that no voting system is fair. What it really says is that we're talking about paired comparison rules. And so what Arrow's theorem says, that whatever you're using paired comparisons with statistics or anything, expect problems to arise. So it's really a theorem applies only to paired comparisons because the IIA is a filter. It says if you don't have paired comparisons, we don't want to look at you. We only look at rules that have paired comparisons. And so Arrow's theorem really tells us there's difficulties. And so if there's difficulties, it starts be careful, problems will occur. So if there's difficulties, we want to find ways to resolve them. Okay, and here we have a hodgepodge of different methods coming from political science, economics, everywhere. I'm going to talk about supermajority rules. That includes majority voting as a special case. A supermajority voting is where you have N voters and you need at least Q votes to win. So a majority vote then is if you have 100 voters, you need 51 or more votes to win. US Senate, you have 100 votes, you need at least 60 to win. Okay, so there's 2. Here's 1, level of significance. If I have 100 data points, 95 of them have to be on your side. For example, in null hypothesis arguments, etc. Or 0.95 NN. Question, these are paired comparisons. Different rules, different weights that you apply we'll be able to say yes or no. And the question I want to ask is, can cycles occur with these type things here? And the answer is yes. In all of them, it's possible to have cycles. Is it possible to have a cycle, for example, where A beats B, 95 to 5, B beats C, C beats D, D beats A, all of them 95 to 5? Well, we're going to find out whether or not that's possible in a few seconds. But in general, cycles are possible. Now, so how can we go about solving that problem? Well, maybe we can try to limit the number of alternatives we're going to consider. Look, if I have only 2 alternatives, I'm not going to have a cycle with the majority vote. If I have a unanimity rule, the NN rule, I don't care how many alternatives I have, I'm never going to get a cycle. Because with unanimity, you get a cycle only if the voters have cyclic preferences. So for each rule in between majority and unanimity, maybe everything goes fine if you have only a certain number of alternatives. And so this is done by Nakamura in the 1970s. And the Nakamura number really is the following. It says that I have n voters. You need q votes. So you take n divided by n minus q. Usually it's a fraction, so you round it up. If it's an integer, it's fine. If it's not an integer, you round it up. And the theorem is that if I have n, or if I have that many or more alternatives, you can have a cycle. Cycles are possible.
Are or are not?
Are. So to avoid cycles, you need to have less than this number, strictly less than this number, to avoid cycles. Okay, and this was proved with combinatoric type arguments. Now, let's take some examples. The US Senate, I have 100 voters. The difference between quota and here, which is the n minus q, is 40. That's 2.5. That rounds up. So if I have 3 alternatives, even with a 60 vote, threshold of 60 votes, you can have A beating B, B beating C, and C beating A. Totally possible. Level of significance. Here I have n. This is what I need for quota. Here's the difference. It's 1 over 0.05, 20. And this says that if I have 20 or more alternatives, even with this high level of significance, it's possible to have a cycle. Now that's a large number of alternatives. And with 20 alternatives, you can understand why we don't see it often in experiments or in the empirical literature, simply because you need so many alternatives for this to occur. But even if you don't have a cycle, the trouble is that it places in question whether you're getting the right outcomes. Because what can cause a cycle, maybe it can hurt the interpretations of the data or of the outcomes. Okay, so this is one approach. Limit the number of alternatives. Here's a second approach. Let's limit the kind of data we can have. Look, if everybody in here says A is better than B is better than C, unanimity, we don't have to worry too much about a cycle. Well, how far away from unanimity can I go so that I will have no cycles in paired comparisons?
That's forcing transitivity.
Pardon?
That's forcing transitivity.
With
Forcing transitivity.
Yeah, forcing transitivity, correct. Exactly. Both of these are forcing transitivity type things. And so if we can limit the data, if the data happens to have, doesn't have certain types of rankings, then the question is that maybe cycles, paired comparisons won't cause cycles. And one of the widest used is the majority vote. It's black single peaked condition. Now, black single peak condition has a technical definition. Anybody interested later, I'll tell you what it is. But right now, I'll just say that if you have 3 candidates, that some candidate is favored enough by all of the voters that no voter ever has that candidate bottom ranked. Okay? So there's some candidate that is favored enough that nobody will have it at the bottom. If you have that situation, you never will have it cycle. Ward, in a paper that isn't as well known as it should be, it goes a little bit further. Let's suppose that for 3 alternatives, some candidate is really, really good. Okay? Nobody has that person bottom ranked. Some candidate is really, really bad. Nobody has that candidate top ranked. Or third possibility, some candidate is extreme, one extreme or the other, never middle ranked. That if any of those 3 conditions crop up, Ward proved that you can never have a cycle. Now, if you have a cycle, cycles really come from triplets. You know, you put the triplets together and the cyclic type effects in there. And so what did Sen do is he took Ward's condition and extended it. He said, for a majority vote, to avoid a cycle, take a profile, restrict it to any triplet, and one of Ward's conditions have to be satisfied. If that's the case, you won't get a cycle. Okay? And so that's what we have there. Now, the question I want to ask you, we have this and we have this. Both widely used methods. What do they have in common? Is there anything in common? Is there a common story that will explain both of these? And that's where symmetry comes in. If we understand what's the appropriate symmetry group, the appropriate symmetry, these and many, many other conditions, in fact, almost all of the paired comparison literature where you have difficulties, etc., or trying to create examples, become apparent. And so the unifying symmetry argument, I'm going to show you what it is. Now, when you have a cycle, if you have A is better than B, but B is better than C, but C is better than A, but A is better than B, it sounds to me like a spinning wheel, okay? It's just spinning around and around. And so really what happens is, to understand this, I created, and you'll see the symmetry group in a second, I created what I call a ranking wheel. Just a wheel. Now take how many alternatives you have. Let's suppose there's 6 of them. Then put the ranking numbers over here. If I have 10, then uniformly I put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I just have a wheel with the numbers, ranking numbers on the edges. And any way you wish, put down the names of the candidates. I put them in the A, B, C, D, E, F fashion. The wheel, what does it do? Is it gives you the ranking, see? A is in first place, B is in second place, C is in third, D, E, F. Now I'm going to rotate the wheel 60 degrees to the next point. B is now in first place, C is in second, D is in third, E, F, A. And so that's the second ranking. And I continue this all the way through until each candidate is in first place once. And so there's my ranking wheel configuration. In math terms, this is the Z6 group orbit. Now, no candidate is favored because by construction, each candidate is in first place once, each candidate is in second place once, each candidate is in third place once, etc. So no candidate is favored. You give me an argument why Anne is better than all of the rest, and I will just take your argument and slightly adjust it, and it'll show that Barb is the best, or Connie is, or whoever you want. So by symmetry arguments, nobody is favored here. But look at the paired comparisons. The paired comparisons have huge, huge cycles. Look. B is better than C, B is better than C, C is better than B, B is better than C, B is better than C, B is better than C. With this ranking wheel configuration, B beats C by 5 to 1. And in fact, one shy of unanimity. In fact, you will have that A beats B by 5 to 1, B beats C beats D beats E beats F beats A, all by 5 to 1. A huge, huge cycle. Such a huge cycle that if you ever had a vote and you went part way through, you would say, wow, okay, something's going on here. That's close to unanimity, there's nothing wrong. Yes, there is. But this also then leads you to path dependency problems and everything else. Because the order in which you talk about the candidates, the order in which you rank the, compare the candidates will determine the outcome. So you've got path dependency problems, you've got cycles, you have all sorts of issues that arise. So this is called a Z6 orbit from group theory, and it is really a hidden connection among the parts because you wouldn't expect that connection. And in fact, this connection really plays a crucial role in the area. I prove that for any n greater than 2, all possible paired comparison ranking problems, path dependency type issues, cycles type conditions, all of them, that really what they can do is they're due, in a sense of linear algebra, to ranking wheel configurations. That means if you want to create an example where you have a cycle or a path dependency or something, use one of these or part of it. And in fact, it says that all possible ways, even more, not only can I use that to construct examples, but all ways to avoid cycles must limit the number of ranking wheels that are in the data. And I'll illustrate this in a second. And then all ways to resolve this problem must, in some sense, address this ranking wheel effect. So really, the symmetry of the ranking wheel of the Z6 is totally responsible for all of the issues and all of the theorems in the literature. Let's take an example. Here's a ranking wheel configuration for 3 candidates, A, B, C, B, C, A. See, A is in first place, first, second, third, etc., but in a special order. Now let's take a look at Ward's condition. Ward's condition is not satisfied here. Because Ward's condition says either some candidate is not top ranked, well, they're all top ranked, or some candidate is not middle ranked, or some candidate is not bottom ranked. Well, this configuration has all of them. So what does Ward's condition do? Ward's condition says you can't use, your data can't have a ranking wheel in it. That's what it says. That you cannot have that Ward's condition really just says that the data cannot have a ranking wheel configuration inside of it. Let's go to Arrow's theorem. As I showed you, contrary to what we teach our students, Arrow's theorem is really a theorem about beware, if you have paired comparisons, problems can arise. Well, you want to be able to prove problems can arise, or prove his theorem. And if you look at it very carefully, hidden in the proof, hidden in examples, are ranking wheel configurations. So here's an example where we show that a theorem just is there. Here we're a proof of a theorem. So all of these things right here just pop up. We have only Nakamura's number left to do this. So at Nakamura's number, if I have a ranking wheel, I showed you a ranking wheel with 6 candidates, and it had cycles with 5 to 1 outcomes. If I have n candidates, it's just one shy of unanimity. The votes will be n minus 1 to 1. You'll have a cycle with n minus 1 to 1. All right? Now, if I have 2 copies of a ranking wheel, then the tallies of the cycle are going to be 2 times this to this. If I have r copies, it's going to be r times n minus 1 to r tallies. And so what's Nakamura number? Nakamura number is if you have a Qn rule, and you remember I showed you that if you have so many alternatives, then you can have a cycle. Nakamura number is find the value of r so that r times n minus 1, the tally, in other words, I'm having r copies, r times n minus 1 is at least q, which means that it satisfies the rule, and I have enough voters. Rn is less than n. So really, Nakamura number is just a very, very special case of the ranking wheel, again. And in fact, what happens is, as I stated, all results, Nakamura number is the least number of copies of the ranking wheel needed to get a cycle, or the QN rule. And so, as I stated, that all of the paired comparison type problems that crop up, what do is they all can be extended in terms of ranking wheels. I stated earlier that there was no rule, general rule, profile restriction, like Ward's condition and that, for QN rules. There is no. And you have to expect it's going to be strictly in terms of ranking wheels. That's all it is. And so, as I stated, many new results. I created the very first profile conditions, as you were saying, forcing transitivity by allowing only certain types of rankings, which now hold for any QN rule. So these conditions just crop up, and they're all due to symmetry. New theorems for spatial voting. For those who know the terms, core, various other type things. When do you have a core? When is it going to be structurally stable? They all come from ranking wheel type results. And so really, the purpose of this lecture right here, it was to emphasize the power of symmetry groups in understanding what can happen. And really, fortunately, everything extends to more general groups. You have just different groups. I gave you a Z6, but more general groups. For example, if you have 4 candidates and you have voting problems, and what kind of problems can crop up? 4 candidates, A, B, C. Oh, that looks like a box. Oh, we have a symmetry group there. It's called a Klein 4 group. That talks about the symmetries of flipping a box in all sorts of ways. And indeed, by use of that symmetry, you can explain most of the paradoxes that crop up with 4 candidates in voting theory. And it goes on in exactly this way. And really what the statement is, and this is my final statement, it's that key to all of these arguments in group decision theory, whether you're using it in statistical tests, whether you're using it in voting, whether you're using it, I don't care where. Key to all of them, it's that there's some underlying symmetry groups that are there. And the symmetry groups are what cause problems. And therefore, if you want to solve the problems, to get rid of the problems, you have to find ways of getting rid of the negative effect of the ranking wheel or the whatever symmetry group you happen to be looking at. And with that, I thank you. Okay. Any questions anyone has? Yeah.
Partial orders.
Partial order? Yeah, partial orders are more, also has the same thing. But now what you're doing is you have subgroups because this doesn't have the completeness now. And so, but same type of thing goes through. But and as you're well aware, probably more than anyone in the room, you have difficulties with partial orders. And really hidden underneath there are indeed symmetry group type configurations that go on in there. Any other questions on that? Yeah. Okay, we'll take care of it. Part won't get my back. Huh?
In European elections, they usually have many alternatives.
Yeah.
But they're not asked to rank them pairwise, but
That's
to
right.
pick one.
That's right.
So the problems that arise that you have described, how do they manifest themselves in this kind of voting where you only pick the best?
What happens is, she's talking about different things like the list method and various others that they use in Europe around the world where they have a large number over there. And really, since you're not using paired comparisons, you're just using a different symmetry group. So,
the problem where, like, if we ask them to rank them pairwise and got a wheel, right, that's a problem. But we don't do that. And in fact, we use a different type of voting. Is there a problem that translates into this other type
Yes,
of
there
voting?
is.
Yeah.
Yes, they are. They're just different symmetry groups. They're just different because you're talking about different size groups. And since you're talking about different size groups, it turns out, like for example, if you're talking about 4 candidates or, for triplets within there, then you're really using the Klein 4 group to try to understand what happens. The Klein 4 group will explain all possible problems that can crop up. So the delight of this is that I just told you about these symmetry groups for paired comparison. It's just one. Once we start getting into where we're looking at triplets and how triplets are arranged or things like this, and this goes on here in sociology, et cetera, where they're looking at triplets in rankings. And once you start getting into there, you have a different symmetry group that's underneath there, which is compared to the Klein 4 group, and you then see, here's why we're having difficulties. So a theorem like Arrow's theorem goes through. In fact, the theorem like Arrow's theorem, which says you're guaranteed problems with paired comparisons, because that's what it says. It's not what we teach, but that's what it really says. And it doesn't care where these paired comparisons crop up, whether they crop up in statistics or anything else. And the question then is, if you have triplets or anything else, you're just using different symmetry groups. And some of those I haven't looked at yet, but they're there. Yeah. Any other questions?
Well, they sound silly. If UCLA beats USC tomorrow, does that say that this whole ranking of where people stand in the Southern Pac-12 could actually be turned around as a real 10?
Well, let's get a little bit more personal. All right. What happens is I'm from Northwestern University. All right. Now, Northwestern beat Iowa in an overtime, and Iowa went on and beat Penn State. Northwestern beat Michigan State in a triple overtime. And Michigan State went on to beat Ohio. So my argument always is that means that Northwestern should be in the top 2 and go to the bowls. So the answer is yes. The answer to your question is yes. That underlying some of those type things, there are indeed ranking wheel type configurations on there. A path dependency type issue that you have there. You had a question?
Well, I'm just thinking that this doesn't really tell us why people make decisions, right?
No, it doesn't.
How decisions play out.
That's right.
Perhaps,
That is correct. It doesn't say how people make decisions. What it does is it says that when you're trying to create a theory for how people make decisions, what you have to do is be aware that you can have misleading type group decisions if you aren't careful. And this gives exactly the type of theory that tells you where you have the difficulties. Yeah. Any other? Yeah.
So John, this is very different to the treatment in economics and political science textbooks.
Very different.
There's a lot of effort spent on looking at different ways to solve the single peakness, and that's another special case.
Special case of the ranking wheel. It's because a single peaked is a very special case of Ward.
That's right.
And so therefore, single peaked is a very special case that says no ranking wheels are allowed in the data. Very, very different than what's taught in the literature, yeah.
So all of this effort are just these special cases.
Special cases, and that's really, from your other talk that you gave, your inaugural talk here, what happens is that you have a literature and it's full of all kinds of examples to try to solve this. And they don't look like they have anything to do with each other. That's why I chose two things that didn't look like they had anything to do with each other. And the reality is that yes, they're all just special cases of trying to get around this same difficulty. We just have to understand what causes the difficulty. And what causes the difficulty, I'm not telling what people decide, but I'm saying if you have a group, this is what you have to worry about. It's total aggregation type issues, absolutely. Any other? Yes?
We know that you view those, the candidates groups as a symmetry group. But if we consider some other groups, is there any relation of a homomorphism between the groups and the symmetry remains?
Most groups that I've looked at, I can find where it explains a paradox. A paradox in the sense of we didn't expect, we didn't expect this to happen. Now, a lot of the groups really are for higher number of candidates, not for pairs, but for higher number of candidates, for triplets or things like that. If you take the example, if you take the Klein 4 group, whatever that is, then what you can do is you can show that if you look at triplets, you can get A is better than B is better than C, B is better than C is better than D. You get a cycle with triplets all the way around. And higher groups will give you the same thing. And but as I stated, almost every group that I've looked at, I can find exactly where it causes a difficulty in some voting group decision making method. Yeah. Okay.
Thank you very
Yeah.
much, Dan.